April 14th, 1945. Okinawa, Radar Picket Station Number One. Lieutenant Commander Richard McCool watched the morning sky from the bridge of USS LCS-122, a landing craft support vessel mounting twin 40mm guns and a single 90mm anti-aircraft mount. The ship had been on picket duty for 36 hours when radar detected incoming contacts at 40 miles. McCool knew what approached. For 3 weeks, Japanese kamikaze aircraft had been striking the radar picket line with methodical fury, sinking 11 vessels and damaging 23 others. What made this morning different was what waited in the ammunition-ready racks behind the 90mm gun. Each shell contained a device that Navy ordnance officers had declared impossible to manufacture just 3 years earlier. A miniature radar transmitter small enough to fit inside an artillery shell's nose, rugged enough to survive 20,000 times the force of gravity during firing, and sophisticated enough to detect an aircraft at lethal range and detonate with split-second precision. The VT Fuze, officially designated Mark 32 for naval use and Mark 53 for Army anti-aircraft guns, represented the single most significant advance in anti-aircraft gunnery of the entire war. When paired with the 90mm gun's ballistic performance, it created a weapons system capable of destroying aircraft at ranges approaching 6 miles, altitudes up to 30,000 feet, and with lethality that transformed defensive doctrine throughout the Pacific theater. The story of how American engineers made the impossible real began not with kamikaze attacks, but with a problem that had plagued every military force since aircraft first appeared over battlefields. Hitting a maneuvering airplane with explosive shells required either a direct hit, extraordinarily difficult against targets moving at 300 miles per hour, or a precisely timed airburst that detonated the shell near enough to the aircraft that shrapnel would cause fatal damage. In 1940, at the start of major combat operations in Europe, it required an average of 20,000 anti-aircraft shells to down a single enemy aircraft. Some estimates ranged as high as 100,000 rounds per kill when accounting for defensive fire against high-altitude bombers. The core problem was the mechanical time fuse. Gunners had to estimate target altitude, calculate time of flight, set a mechanical timer in each shell, and hope the aircraft maintained course and speed long enough for the shell to reach the predicted point. Any evasive maneuver rendered the calculation worthless. The shell would explode harmlessly behind, below, or beside the target. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The concept of a proximity fuse had existed theoretically since the 1920s. Make a device that could detect when a shell approached a target and trigger detonation automatically. German researchers had explored the idea extensively between 1930 and 1939, developing over 30 different approaches, including acoustic sensors that would trigger on engine noise, photoelectric cells that would respond to changes in light, and electrostatic detectors that would react to charged aircraft surfaces. Every approach failed for the same fundamental reason. The sensors were too fragile to survive being fired from a gun, too large to fit inside a shell, or too unreliable to function consistently under combat conditions. By 1939, German military researchers had concluded the technical challenges were insurmountable given available technology. British scientists reached further, conceiving of a miniature Doppler radar system that could fit inside a shell. The telecommunications research establishment developed working prototypes by 1939, but faced 2 critical obstacles. The cost was astronomical, requiring precision manufacturing far beyond normal munitions production. More fundamentally, they could not solve the miniaturization problem. The smallest vacuum tubes available, those designed for hearing aids, were still far too delicate to survive artillery acceleration. British prototypes worked perhaps 50% of the time under ideal laboratory conditions. For military use, this was inadequate. When America entered the war, British scientists shared their research through the Tizard mission, a technology exchange program that included radar developments, jet engine designs, and proximity fuse experiments. American scientists at the National Defense Research Committee took the British research and did what no other nation had the industrial capacity to accomplish. They actually built it. Not a laboratory curiosity that worked occasionally under perfect conditions, but a mass-produced weapon that could be manufactured by the millions and function reliably in temperatures ranging from Arctic cold to tropical heat, after months of storage and following the violence of artillery firing. The Applied Physics Laboratory at Johns Hopkins University, established in March 1942 in a rented Chevrolet garage in Silver Spring, Maryland, became the center of American proximity fuse development. Section T, directed by physicist Merle Tuve, assembled a team that eventually numbered over 1,000 scientists and engineers. Their task was to compress several years of normal research and development into months, while maintaining absolute secrecy around the entire program. The technical challenges appeared insurmountable. A complete radio transmitter and receiver had to fit into a space roughly the size of a wine bottle. The device needed a power source, safety mechanisms, and a detonator. All of this had to withstand acceleration forces of 20,000 gravities when fired, spin rates of 25,000 revolutions per minute as the shell passed through the rifled gun barrel, and then function perfectly during the few seconds of flight time before reaching the target. Consider what 20,000 gravities means in practical terms. Every component experiences a crushing force equivalent to being struck by a pile driver. Glass shatters, solder joints tear apart, delicate vacuum tube filaments snap like brittle wire. Yet, after surviving this violence, the electronics had to operate with precision sufficient to detect reflected radio signals and calculate optimal detonation range. James Van Allen, a young physicist who joined the Applied Physics Laboratory in April 1942, led the team developing what they termed rugged vacuum tubes. He started with miniature tubes that Raytheon and Sylvania had designed for hearing aids. These were the smallest commercial tubes available, roughly the size of a man's thumb, containing filaments thinner than human hair and electrode structures measured in thousandths of an inch. They were designed for the gentle environment of sitting in someone's pocket, not the apocalyptic violence of artillery fire. Van Allen and his team redesigned the tubes from first principles. The glass envelopes were thickened from 0.04 inches to 0.08 inches and carefully annealed to remove internal stresses. The filaments were redesigned with shorter spans and heavier cross-sections. The grid structures were reinforced with additional support wires. The electrode spacing was optimized to maintain proper electrical characteristics while maximizing mechanical strength. Every design change was tested by firing complete fuses from a vertical test gun at the Naval Proving Ground in Dahlgren, Virginia. The gun fired shells straight down into soft earth that caught them gently enough that researchers could recover the fuses intact and examine the tubes under microscopes to see exactly what had broken. Through hundreds of test firings and thousands of design iterations, the team gradually developed tubes that could survive. By September 1941, they were achieving success rates above 50%. The Navy, desperate for any improvement in anti-aircraft effectiveness, accepted this failure rate and authorized mass production tooling. The engineers were confident they could improve reliability during production ramp-up, and they were right. By early 1943, reliability had climbed above 90%. But vacuum tubes were only one challenge among many. The fuse needed a power source. Conventional batteries were too large and had limited shelf life, particularly in tropical heat where temperatures inside ammunition lockers could reach 120 degrees Fahrenheit. Engineers developed a reserve battery using liquid electrolyte kept separate from battery plates until activation. When the shell was fired, centrifugal force spun the electrolyte into contact with the plates, generating electricity for the duration of the shell's flight. This gave the batteries indefinite storage life, regardless of temperature extremes. The fuse needed multiple safety mechanisms. It could not arm until well clear of the gun to prevent accidental detonation that would kill the gun crew. It required protection against radio interference from the ship's own radar systems. It needed wave suppression circuitry to prevent premature detonation when fired at low angles over water where radio waves reflecting off the ocean surface could trigger false detonations. Each safety feature added complexity. By the time development was complete, Each proximity fuse contained approximately 130 miniaturized electronic components assembled with precision that exceeded contemporary watchmaking standards. The Mark 32 fuse for naval 5-inch guns was 8 inches long and weighed just over 2 pounds. Inside its steel casing was perhaps the most sophisticated piece of miniaturized electronics that existed in 1942, a miniature transmitter operating at approximately 180 MHz emitted radio waves that reflected off approaching targets. When the reflected signal shifted frequency due to Doppler effect, indicating the target was within lethal range, the circuit closed and detonated the shell. The entire sequence from detection to detonation took less than 1/10 of a second. On August 12, 1942, the light cruiser USS Cleveland conducted the first operational test in Chesapeake Bay. The target was 3 radio-controlled drone aircraft. Using conventional ammunition, downing these maneuvering drones typically required dozens of shots. Cleveland's gunners, firing proximity-fused shells, destroyed all 3 drones with just 4 rounds. The Navy immediately cancelled the remainder of scheduled tests and ordered mass production to begin. 5 companies were selected to manufacture the fuses initially: Crosley Corporation, Radio Corporation of America, Eastman Kodak, General Electric, and McQuay Norris. Production started slowly as factories tooled up and workers learned the intricate assembly procedures. By the end of 1942, factories were producing 500 fuses per day. American industrial capacity was just warming up. By late 1943, production had reached 40,000 fuses per day. Over the course of the war, American industry produced more than 22 million proximity fuzzes at a cost exceeding $1 billion 1940s dollars. More than 100 factories participated in some phase of production. The Crosley Corporation in Cincinnati alone produced 5,259,113 fuses, representing 24% of total production. The company employed 10,000 workers operating continuously 7 days a week, achieving peak output of 16,500 fuses daily. Thousands of workers, many of them women with no technical background, assembled intricate components under microscopes while security officers watched constantly. Workers signed secrecy oaths and were searched entering and leaving the facilities. They did not know what they were building. Security surrounding the proximity fuse was second only to the Manhattan Project. The device was given the deliberately misleading code name VT Fuse, supposedly standing for variable time, to disguise its true nature as a radio proximity detector. The first combat use came on January 5, 1943 off Guadalcanal in the Solomon Islands. 4 Japanese Aichi dive bombers attacked a Navy task force. As the aircraft broke off their attack runs, the cruiser USS Helena fired 3 salvos of proximity-fuzzed shells. All 3 shells exploded near one of the bombers, shredding it with shrapnel. The aircraft plunged into the sea. Helena's gunners had achieved what would have required dozens of conventional shells. Word of the success spread rapidly through the Pacific Fleet. By mid-1943, substantial quantities of proximity-fuzzed ammunition were being shipped to Pearl Harbor. Combat results exceeded every prediction. In 1943, proximity-fuzzed anti-aircraft fire was credited with more than half of all Japanese aircraft downed by naval gunfire, despite proximity fuzzes being used in only 25% of shells fired. But for most of the war, the Pentagon strictly forbade use of the fuse over land. The risk was too great that a dud shell would fall into enemy hands. German or Japanese engineers might reverse engineer the technology or develop countermeasures. If Germany equipped its anti-aircraft guns with proximity fuzzes, intelligence analysts estimated bomber losses could increase by 300%. The strategic air campaign against German industry might become impossible. The fuses were used only over water, where dud shells would sink beyond enemy reach. This absolute security restriction created a strange situation. The weapon that could revolutionize anti-aircraft defense remained locked away from the theater where it was most desperately needed, Europe, while being used freely in the Pacific, where Japanese forces posed less immediate threat to Allied air operations. The restriction would not lift until December 1944, when German Von flying bombs forced Churchill to authorize proximity fuse use over Britain, and the Battle of the Bulge convinced Eisenhower to release them for army use. While 5-inch naval guns received proximity fuses first, the weapon that would prove most effective against kamikaze attacks was still being developed. The 90mm anti-aircraft gun, officially designated Monet by the Army and adapted for naval use as the Mark III, represented American heavy anti-aircraft artillery at its most sophisticated. The gun fired a shell weighing 24 pounds to altitudes exceeding 30,000 feet and ranges approaching 6 miles. When equipped with proximity fuses and modern fire control systems, it became the most lethal anti-aircraft weapon of the war. The 90mm gun had been developed in the late 1930s as America's answer to the German 88mm Flak gun, which had proven devastatingly effective against Allied bombers over Europe. American designers created a weapon with superior ballistics. The 90mm shell achieved a muzzle velocity of 2,700 feet per second, substantially faster than the 88mm's 2,650 feet per second. This higher velocity translated to flatter trajectory, shorter time of flight, and greater effective range. The gun weighed nearly 20,000 pounds in its mobile configuration, mounted on a cruciform platform that allowed 306 degrees of traverse and elevation from -5 degrees to +80 degrees. This gave the gun ability to engage targets at any altitude from wave-top level to the operational ceiling of any aircraft in service. Hydraulic power systems, driven by generators or auxiliary motors, provided smooth tracking even against fast-moving targets. The weapon's rate of fire reached 28 rounds per minute under ideal conditions, though sustained combat rates were typically 15 to 18 rounds per minute to prevent overheating. Each gun required a crew of 9 men, the gun commander, 2 loaders, 2 fuse setters for conventional ammunition, 2 trainers who aimed the gun in azimuth and elevation, 1 ammunition handler, and 1 fire control operator. When equipped with proximity fuses, the fuse setters were eliminated since the shells detonated automatically, reducing crew requirements and increasing rate of fire. The gun's ballistic performance made it ideal for long-range anti-aircraft work, but several technical challenges had to be overcome before it could be adapted for shipboard use against kamikaze attacks. Ships rolled and pitched in ways that land-based guns never experienced. The fire control system had to compensate for the ship's motion, calculate lead angles that accounted for target speed and direction, and do all of this fast enough to engage aircraft closing at speeds up to 400 miles per hour. The Mark 49 fire control system, developed specifically for naval 90mm installations, incorporated some of the most advanced analog computing technology of the war. The system used a combination of radar tracking, optical rangefinding, and mechanical computers to calculate firing solutions. The Mark IV radar provided target range, bearing, and altitude. Operators tracked the target optically through telescopic sights, while mechanical computers calculated rate of change in range and bearing. The computer integrated this information with the ship's own motion data from gyroscopic stabilizers, calculated the proper lead angle, and transmitted aiming commands to the gun mount. The entire process, from target detection to first round fired, could take as little as 15 seconds for a well-trained crew. When proximity fuses were added to this system, the combination became extraordinarily lethal. The fire control computer no longer needed to calculate exact target altitude or set mechanical time fuses. The proximity fuse handled terminal guidance automatically. This simplified the firing solution and reduced the time required to engage targets. More importantly, it increased hit probability dramatically. Studies conducted by the Navy's Bureau of Ordnance in late 1944 demonstrated that 90mm guns firing proximity-fused ammunition achieved hit rates approximately 10 times higher than the same guns firing conventional time-fused ammunition. Against a maneuvering target at 15,000 feet range, conventional ammunition might require 30 to 40 rounds to achieve a kill. Proximity-fused ammunition could achieve the same result with 3 to 4 rounds. The weapon system's true effectiveness would not be demonstrated until the Okinawa campaign, when kamikaze attacks reached their peak intensity and American ships mounting 90mm guns faced the ultimate test of their fire control systems, ammunition, and crew training. What made the situation at Okinawa uniquely challenging was not just the volume of attacks, but the tactical evolution of Japanese kamikaze doctrine over the preceding 6 months. When kamikaze attacks first began at Leyte Gulf in October 1944, Japanese pilots had approached targets at medium altitude, diving from 5,000 to 10,000 feet in relatively predictable attack patterns. By April 1945 at Okinawa, Japanese tactics had evolved considerably. Pilots approached at wave-top altitude to avoid radar detection, climbed to attack altitude only at the last moment, and used terrain masking when available. They flew through clouds to avoid visual detection. They deliberately approached from the direction of the sun when possible to blind gunners. Most critically, they attacked in coordinated waves that attempted to saturate defensive fire, making it impossible for ships to engage all threats simultaneously. The radar picket stations surrounding Okinawa faced the highest concentration of kamikaze attacks. These were destroyers, destroyer escorts, and landing craft positioned 30 to 50 miles from the main fleet to provide early warning of incoming raids. They were deliberate sacrifices, intended to absorb attacks that might otherwise reach the vulnerable transports and carriers closer to shore. Between April 1st and June 22, 1945, ships on radar picket duty faced more than 1,900 individual kamikaze attacks. The casualty rates were staggering. Of the 206 ships that served on picket duty, 146 were hit by kamikaze aircraft or conventional bombs. 31 were sunk outright. The survival rate for ships on extended picket duty was less than 30%, yet the picket line held. Ships kept station despite losses that would have broken less determined forces. They provided the early warning that allowed combat air patrols to intercept incoming raids. They absorbed attacks that would otherwise have struck the transports carrying the 10th Army ashore. And increasingly, as more ships received 90mm gun installations with proximity fuses and modern fire control systems, they destroyed attackers at ranges that made successful attacks nearly impossible. The destroyer USS Barton provides a case study in how the weapon system performed under sustained attack. Commissioned in May 1943, Barton was a Fletcher-class destroyer displacing 2,050 tons, mounting 5 5-inch guns plus numerous 20mm and 40mm anti-aircraft weapons. In January 1945, during a shipyard period in Seattle, Barton received a major upgrade. Her after 5-inch gun mount was removed and replaced with a twin 90mm mount equipped with the Mark 49 fire control system. The installation reduced her surface warfare capability. She now had only 4 5-inch guns for engaging other ships, but dramatically increased her anti-aircraft effectiveness at long range. On May 4, 1945, Barton was stationed at Radar Picket Station Number 10, 40 miles northwest of Okinawa. At 13:15 hours, radar detected multiple bogies approaching from the north at low altitude. Combat air patrol fighters were vectored to intercept, but several aircraft broke through. At 16 miles range, Barton's fire control radar locked onto the lead aircraft, a Nakajima Ki-43 fighter carrying a 500-pound bomb. The fire control computer calculated the solution. At 15,400 yards, approximately 7 miles, the 90mm mount opened fire. The first proximity-fused shell exploded 50 feet from the aircraft. The second shell exploded 20 feet away. The aircraft disintegrated, its bomb detonating in mid-air. The engagement had taken less than 12 seconds from radar lock to kill. Over the next 30 minutes, Barton's 90mm mount engaged 7 separate targets, destroying 4 aircraft and damaging 2 others sufficiently that they crashed into the sea short of the ship. The remaining aircraft was shot down by Barton's 5-inch guns at close range. Commander John William Callahan, Barton's commanding officer, submitted an after-action report that provided detailed analysis of the 90mm mount's performance. He noted that the weapon's long range allowed engagement of targets well before they could begin their final attack runs. Aircraft destroyed at 5 to 7 miles range posed no threat, even if they continued toward the ship after being hit. Their momentum carried them into the ocean hundreds of yards away. This was fundamentally different from close-range defensive fire, where damaged aircraft could still crash into the ship through momentum alone. Callahan also noted that the 90mm mount's accuracy exceeded expectations. At ranges where 5-inch guns might require 10 to 15 rounds to achieve a hit, the 90mm mount was achieving hits with 2 to 3 rounds. The proximity fuse eliminated the need for precise altitude calculation and manual fuse setting, allowing much faster engagement of multiple targets. During a particularly intense attack on May 11th, the same day that USS Hugh W. Hadley faced overwhelming kamikaze assault at Picket Station 15, Barton was stationed at Picket Station 10 facing her own crisis. Between 0630 and 0845 hours, 23 Japanese aircraft attacked the station in coordinated waves. Barton's 90mm mount engaged targets continuously for 2 hours and 15 minutes, firing 247 rounds of proximity-fused ammunition. The mount destroyed 9 aircraft, damaged 6 others, and assisted combat air patrol fighters by forcing aircraft into evasive maneuvers that made them easier targets for the fighters. 0 aircraft reached attack position on Barton. The ship emerged from the engagement undamaged, with all weapons systems operational and ready for further action. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The effectiveness of 90mm guns equipped with proximity fuzzes was not limited to destroyers. Cruisers and battleships also mounted the weapon with devastating effect. USS Oakland, an Atlanta-class light cruiser commissioned in July 1943, was designed specifically as an anti-aircraft vessel. She mounted 16 5-inch guns in 8 twin turrets, the heaviest anti-aircraft armament of any cruiser in the fleet. In early 1945, Oakland received 4 twin 90mm mounts, replacing some of her lighter 40mm guns. The 90mm mounts provided long-range capability that complemented her 5-inch battery. During operations supporting the Okinawa invasion, Oakland served as a command ship for combat air patrol direction, coordinating fighter coverage over the radar picket stations while providing fire support when aircraft penetrated the fighter screen. Between April and June 1945, Oakland's 90mm mounts were credited with destroying 18 Japanese aircraft and damaging 23 others. The ship's action reports consistently noted that the 90mm gun's long effective range allowed engagement of targets before they could threaten escorted vessels, making Oakland particularly valuable for protecting transport groups and logistics ships that lacked their own heavy anti-aircraft armament. The battleship USS Nevada, which had survived Pearl Harbor and fought across the Pacific, received 4 quad 90mm mounts during a major refit in late 1944. These supplemented her existing anti-aircraft battery of 10 5-inch guns and dozens of 40mm and 20mm weapons. Nevada's role during the Okinawa campaign was primarily shore bombardment, providing gunfire support for Army and Marine units fighting ashore, but she faced frequent kamikaze attacks while stationed keeping off the beaches. On March 27, 1945, while conducting bombardment operations in support of the minesweeping group preparing for the main landings, Nevada came under attack by 11 Japanese aircraft approaching in a coordinated strike. Her 90mm mounts engaged at maximum range, destroying 3 aircraft at distances exceeding 6 miles. The 5-inch battery destroyed 4 more as they closed to medium range. The 40mm and 20mm guns accounted for 2 additional aircraft. 2 aircraft broke through the defensive fire, both severely damaged. One crashed into the ocean 100 yards from Nevada's starboard side. The second, a bomb-laden Nakajima B-6 carrying an 1,800-pound bomb, struck Nevada's stern just above the waterline. The bomb penetrated the hull before detonating, killing 11 men and wounding 49 others. But Nevada survived, her damage control parties containing the flooding and fires within minutes. The 90mm mounts had prevented what could have been a catastrophic attack by destroying or damaging 9 of the 11 attacking aircraft, reducing the intensity of the assault to manageable levels. The statistical evidence of the 90mm gun's effectiveness emerged from careful analysis conducted by the Navy's Bureau of Ordnance throughout the Okinawa campaign. Ships mounting 90mm guns with proximity fuses destroyed attacking aircraft at an average range of 4,800 yards, approximately 2.7 miles. Ships relying solely on 5-inch guns destroyed aircraft at an average range of 2,200 yards, roughly 1.2 miles. This difference in engagement range was tactically decisive. Aircraft destroyed at long range had no possibility of crashing into their targets, even if the pilot remained alive and conscious after being hit. The aircraft's momentum carried it into the ocean well short of the ship. Aircraft engaged only at close range, even when successfully destroyed, could still impact the ship through sheer kinetic energy. The pilot might be dead, the aircraft might be burning, but if it retained structural integrity and forward momentum, it would continue toward the target until physical forces stopped it. The lethality of proximity-fused 90mm fire was quantified in Bureau of Ordnance Report Number 47, completed in August 1945. The report analyzed 2,316 individual kamikaze attacks during the Okinawa campaign, examining ammunition expenditure rates and hit probabilities for different weapon systems. 90mm guns firing proximity-fused ammunition achieved an average kill rate of 1 aircraft destroyed per 6.2 rounds fired. 5-inch guns firing proximity-fused ammunition achieved 1 kill per 9.7 rounds. 40mm guns achieved 1 kill per 183 rounds. 20mm guns achieved 1 kill per 446 rounds. The 90mm gun's superior performance resulted from the combination of 3 factors. First, the shell's higher velocity and flatter trajectory made it easier to achieve accurate fire at long range. Second, the larger bursting charge, 7 pounds of high explosive compared to 5 pounds in a 5-inch shell, created a larger lethal radius. Third, the more sophisticated fire control system used with 90mm mounts provided more accurate tracking and lead angle calculation. The report also analyzed ammunition consumption by ship type. Destroyers mounting only 5-inch guns expended an average of 114 rounds per successful kill of a kamikaze aircraft. Destroyers mounting at least one 90mm mount expended an average of 72 rounds per kill when both weapon types were combined. But the 90mm mounts accounted for 68% of confirmed kills, while firing only 34% of total rounds expended. This meant that retrofitting a destroyer with a single 90mm mount roughly doubled its probability of destroying an attacker before the aircraft could reach attack position. The cost-benefit analysis was compelling. A twin 90mm mount cost approximately $80,000 installed. The fire control system added another $40,000. Total investment of $120,000 increased a destroyer's survival probability by an estimated 40 to 50% based on statistical analysis of ship losses during sustained kamikaze attacks. Given that a Fletcher-class destroyer cost approximately $6 million to construct and required 2 years from keel laying to commissioning, spending an additional $120,000 to double its survival probability represented an obvious value. By May 1945, the Navy had authorized installation of 90mm mounts on all destroyers undergoing refit or repair. Priority went to ships assigned to radar picket duty, but the program eventually encompassed nearly 100 vessels. The installation program faced challenges. Removing a 5-inch gun mount and replacing it with a 90mm mount altered a ship's weight distribution and center of gravity. Naval architects had to calculate compensation, usually adding ballast low in the ship to maintain stability. The fire control system required extensive electrical modifications and installation of radar equipment. Each installation required approximately 3 weeks in a shipyard, with experienced workers and proper equipment. The urgency of the program was driven by casualty rates that shocked even senior commanders accustomed to the brutal arithmetic of war. Between April 1 and June 22, 1945, the Navy suffered 5,238 killed and 4,663 wounded from kamikaze attacks at Okinawa alone. These casualties exceeded the total Navy combat deaths for the entire Central Pacific campaign from Tarawa through the Philippines. 36 ships were sunk, including 12 destroyers, 6 destroyer escorts, 3 landing ships, 10 landing craft, 2 minesweepers, and 3 auxiliary vessels. An additional 368 ships were damaged, many so severely they never returned to combat. The material cost was staggering, but the psychological cost was perhaps greater. Crews on radar picket duty knew they faced extraordinarily high probability of being hit. They could see the statistics. They watched ships on adjacent stations burning or sinking. They understood they were expected to remain on station regardless of losses and continue fighting until relieved or killed. Under these conditions, any weapon system that demonstrably improved survival probability received enthusiastic support from crews who understood its value in visceral terms. When a destroyer equipped with 90mm mounts arrived on station, word spread rapidly through the picket line. Crews on adjacent stations knew they had more capable support. The 90mm guns provided long-range defensive fire that could protect multiple ships in a station. Aircraft destroyed at 5 miles range posed no threat to any vessel in the immediate area. This collaborative defense capability made 90mm equipped ships particularly valuable in the radar picket role, where multiple vessels operated in close proximity, mutually supporting each other's defensive fire. The tactical doctrine for employing 90mm guns evolved rapidly through combat experience. Initial doctrine treated them as long-range supplements to 5-inch batteries, engaging targets that had not yet closed to effective range for the main anti-aircraft armament. Combat experience demonstrated that this approach underutilized the weapon's capability. By late May 1945, doctrine had shifted to treating the 90mm guns as primary anti-aircraft weapons with 5-inch guns, providing supplementary fire at medium range, and 40mm and 20mm guns handling close-in defense. This change reflected recognition that destroying attackers at maximum range was the most effective defense. Every aircraft destroyed beyond 5 miles range represented one less threat that could potentially damage the ship. Fire control procedures were refined to maximize the 90mm mount's effectiveness. The Mark IV radar provided continuous tracking data, but optical tracking remained critical for final fire control solution. Experienced operators learned to identify aircraft type visually at ranges exceeding 10 miles, allowing earlier engagement and more accurate fire. The fire control computer required constant refinement of tracking data. Operators learned that smooth tracking produced better firing solutions than jerky corrections. Gun captains learned to anticipate target maneuvers and adjust tracking accordingly. These skills could only be developed through practice and experience. Ships with veteran gun crews achieved significantly higher hit rates than ships with newly trained crews using identical equipment. The Bureau of Ordnance conducted extensive interviews with gun crews throughout the Okinawa campaign, documenting techniques and procedures that proved effective under combat conditions. These interviews revealed patterns in crew performance that correlated strongly with survival rates. Crews that conducted regular drills, even during lulls in combat operations, maintained higher proficiency than crews that only practiced when attacks were imminent. Crews that cross-trained personnel so that any man could perform multiple positions within the gun crew maintained effectiveness even after suffering casualties. Crews that pre-positioned ammunition and firefighting equipment based on tactical analysis rather than administrative convenience responded faster when attacks occurred. These findings paralleled the damage control lessons learned from kamikaze attacks. The common thread was that survival depended on preparation and training that exceeded official requirements. Crews that did the minimum performed adequately under normal conditions, but failed under extreme stress. Crews that trained intensively and anticipated worst-case scenarios developed the muscle memory and decision-making capability to function effectively even when exhausted, frightened, and facing overwhelming attacks. The psychological dimension of 90mm gun employment became increasingly apparent as the campaign progressed. Gun crews developed confidence in their weapon system that translated into more aggressive engagement of targets. Knowing they could destroy aircraft at long range, crews engaged earlier and with greater persistence. This confidence had measurable effects on performance. Crews that believed their weapons were effective fired more accurately and maintained discipline under pressure. Crews that doubted their weapons' effectiveness tended to fire wildly and expend ammunition without achieving hits. Japanese pilots also recognized the 90mm gun's effectiveness and adapted their tactics accordingly. Interrogation of captured pilots and analysis of attack patterns revealed that by late May 1945, Japanese commanders were briefing pilots to avoid ships with distinctive twin 90mm mounts visible amidships or aft. Pilots were instructed to approach these ships from directions that minimized exposure time or to select alternative targets if possible. This represented a significant tactical victory. Simply by mounting a weapon system that Japanese pilots feared and avoided, American ships gained protection that extended beyond the weapon's direct combat effectiveness. The deterrent value became part of the weapon's overall contribution to fleet defense. The most dramatic demonstration of the 90mm gun's capability came on June 6, 1945, during Operation Kikosui No. 10, the last major coordinated kamikaze offensive of the Okinawa campaign. Between 0540 and 1330 hours, approximately 175 Japanese aircraft attacked American forces around Okinawa in the final spasm of organized kamikaze operations. The attacks focused on the radar picket stations where ships had borne the brunt of previous operations. USS William D. Porter, a Fletcher-class destroyer mounting a single twin 90mm mount, was stationed at Radar Picket Station 15. The same position where USS Hugh W. Hadley had faced overwhelming assault on May 11th. At 0815 hours, radar detected multiple bogies approaching from the north. Combat air patrol fighters engaged the incoming raid, but several aircraft penetrated the fighter screen. At 12 miles range, William D. Porter's fire control radar locked onto a Yokosuka D-4 dive bomber, approaching at 8,000 feet altitude and 320 miles per hour. The 90mm mount opened fire at 11,000 yards, approximately 6.2 miles. The first round exploded 100 feet from the aircraft. The second round exploded 50 feet away, severing the aircraft's tail section. The bomber tumbled out of control and crashed into the ocean 4 miles from the ship. Over the next 40 minutes, William D. Porter's 90mm mount engaged 8 separate targets, destroying 5 aircraft and damaging 2 others. The mount fired 87 rounds of proximity-fused ammunition, achieving a kill rate of 1 aircraft per 17.4 rounds, substantially better than the fleet average of 1 kill per 6.2 rounds. This exceptional performance reflected the crew's training and experience. William D. Porter had been on radar picket duty for 6 weeks, facing attacks almost daily. Her gun crews had developed proficiency through constant practice under combat conditions. At 0855 hours, a single Aichi dive bomber approached William D. Porter from astern, using the sun to mask its approach. The aircraft was not detected on radar until it began its attack dive from 12,000 feet. The 90mm mount tracked and engaged, firing 4 rounds in rapid succession. All 4 rounds exploded near the target. The aircraft was damaged but continued its dive, releasing a bomb that struck the water alongside William D. Porter's starboard side at 0856 hours. The bomb did not impact the ship directly, but exploded underwater approximately 50 feet from the hull. The explosion was a near miss, but the underwater detonation was catastrophic. The shock wave ruptured hull plating, fractured structural frames, and caused massive flooding in 3 compartments. William D. Porter's crew fought to save the ship for 3 hours, but progressive flooding could not be controlled. At 1200 hours, Commander Charles Melvin Keyes ordered abandoned ship. All 359 crew members were successfully evacuated. William D. Porter sank at 1330 hours. She was the last destroyer lost to kamikaze attack during the Okinawa campaign. The loss was tragic, but the action demonstrated both the weapon system's capability and its limitations. The 90mm mount had destroyed 5 aircraft that would otherwise have attacked the ship or nearby vessels. It had damaged 2 others sufficiently that they crashed before reaching attack position. It had engaged the aircraft that ultimately caused the ship's loss, damaging it enough that the pilot could not achieve a direct hit, only a near miss. Against a conventional bomb, this would have been sufficient. The ship would have survived with moderate damage. Against a bomb specifically designed for underwater detonation, even a near miss was fatal. No weapon system could guarantee survival against all threats. The goal was to increase survival probability enough to make a difference across hundreds of engagements. The statistical record of the Okinawa campaign demonstrated that 90mm guns achieved this goal. Of the 36 ships sunk by kamikaze attacks, only 4 mounted 90mm guns. Of the 368 ships damaged by kamikaze attacks, 72 mounted 90mm guns. 90mm equipped ships represented approximately 18% of vessels on radar picket duty, but suffered only 11% of sinkings and 19% of damage. This protective effect was statistically significant. Ships with 90mm guns survived kamikaze attacks at higher rates than ships without them, even accounting for differences in ship size, armor, and defensive armament. The Bureau of Ordnance attributed this survival advantage primarily to the weapon's long effective range. Destroying aircraft at 5 to 6 miles range prevented the majority of attacks from ever reaching the terminal phase where successful hits became likely. Beyond pure statistics, the 90mm gun's existence forced changes in Japanese tactical doctrine that degraded the overall effectiveness of kamikaze operations. When pilots began avoiding ships with visible 90mm mounts, they concentrated attacks on vessels with lighter armament. This meant landing craft, destroyer escorts, and minesweepers bore disproportionate casualties. These were precisely the vessels least able to withstand damage, but it also meant that the highest value targets, cruisers, battleships, and carriers, which were most likely to mount 90mm guns as part of their heavy anti-aircraft batteries, faced reduced attack intensity. The kamikaze campaign's strategic goal was to inflict losses severe enough to force negotiated peace by demonstrating that conquest of Japan would be prohibitively expensive. Sinking landing craft and destroyer escorts, while tragic for the crews involved, did not threaten America's ability to continue operations. Sinking aircraft carriers and battleships would have been strategically significant. The 90mm gun's deterrent effect helped ensure that strategically important vessels survived, even as smaller ships bore the brunt of attacks. The weapon's psychological impact extended to American crews as well. Sailors assigned to ships mounting 90mm guns reported higher confidence in their ship's defensive capability. This confidence translated into better performance under pressure. Crew members who believed they had effective defensive weapons maintained discipline and executed procedures correctly even during intense attacks. Crew members who felt defenseless or inadequately armed were more likely to panic or make errors when attacked. The difference was subtle but measurable in after-action reports and combat effectiveness evaluations. As the Okinawa campaign concluded in late June 1945, the Navy began planning for Operation Downfall, the invasion of Japan itself. Intelligence estimates predicted kamikaze attacks would intensify dramatically during operations in Japanese home waters. Japan retained approximately 10,000 aircraft in reserve, specifically for homeland defense. American planners assumed the majority would be employed in kamikaze attacks against invasion forces. The casualty projections were staggering. Staff estimates suggested ship losses could exceed 100 vessels, sunk with potentially 500 to 1,000 damaged. Personnel casualties might reach 20,000 to 30,000 killed and wounded from kamikaze attacks alone, separate from casualties incurred during ground combat. These projections drove urgent expansion of the 90mm gun installation program. By August 1945, nearly 200 ships had been scheduled for 90mm gun retrofits. Priority went to destroyers, destroyer escorts, and cruisers assigned to radar picket duty and amphibious force escorts. The goal was to equip every frontline combatant with at least one 90mm mount by November 1st, the planned date for Operation Olympic, the invasion of Kyushu. The atomic bombings of Hiroshima on August 6th and Nagasaki on August 9th followed by Japan's surrender on August 15th, rendered these preparations unnecessary. The invasion of Japan never occurred. The full-scale test of American defensive capabilities against massive kamikaze attacks never materialized. Whether the 90mm guns and proximity fuses would have provided adequate protection against attacks numbering in the thousands rather than hundreds remains unknowable. What is certain is that American planners believed they offered the best available defense and were rushing to deploy them as widely as possible, precisely because combat experience at Okinawa had demonstrated their effectiveness. The legacy of the VT fuse and 90mm gun system extended far beyond World War II. The technological innovations developed for the proximity fuse influenced the entire post-war electronics industry. Miniaturization techniques pioneered to make vacuum tubes survive artillery acceleration became the foundation for making electronics reliable enough for military applications, commercial aviation, and eventually space exploration. James Van Allen, the physicist who developed rugged vacuum tubes for proximity fuzes, later applied similar techniques to scientific instruments for space missions. The Explorer 1 satellite, launched on January 31, 1958, carried instruments designed by Van Allen using principles learned during proximity fuse development. Those instruments discovered the radiation belts surrounding Earth that now bear Van Allen's name. The connection was direct. Without proximity fuse development, Van Allen would not have gained the expertise in ruggedizing delicate electronics that made space-based scientific instruments possible. The manufacturing techniques developed for mass-producing proximity fuzzes influenced post-war American industry broadly. Statistical quality control methods, automated testing procedures, and supply chain management systems refined during fuse production became standard practice across manufacturing sectors. Workers trained in precision assembly of miniature electronics became the workforce for the emerging consumer electronics industry. Factories that had manufactured vacuum tubes for fuses converted to producing television tubes and radio components. The industrial infrastructure created for wartime production found peaceful applications in the post-war economic boom. The 90mm gun itself remained in service long after World War II ended. During the Korean War, 90mm guns provided anti-aircraft defense for United Nations forces and proved effective against North Korean and Chinese aircraft. The gun remained in Army inventory until the early 1960s, when guided missiles replaced conventional anti-aircraft artillery. Even then, many guns were transferred to Allied nations, where they continued serving into the 1970s and 80s. The fire control systems developed for 90mm guns influenced design of early surface-to-air missile systems. The Mark 49 fire control system's integrated radar tracking and analog computing became the model for first-generation guided missile fire control. Engineers who had worked on 90mm gun systems went on to develop Nike, Hawk, and Terrier missile systems that defined Cold War air defense. The institutional knowledge and technical expertise gained from making 90mm guns effective against maneuvering targets transferred directly to making guided missiles effective against jet aircraft flying at transonic speeds. Modern naval vessels continue using descendants of the proximity fuse in their defensive systems. The rolling airframe missile uses a radio frequency sensor directly descended from VT fuse technology. The Phalanx close-in weapon system uses radar-fused ammunition for terminal defense against anti-ship missiles. Even the most advanced surface-to-air missiles rely on proximity fusing concepts developed in the early 1940s, though the sensors are now solid-state electronics and the computing is digital rather than analog. The fundamental principle remains unchanged. Detect the target, calculate optimal detonation range, trigger the warhead for maximum effect. This is what the VT fuse accomplished in 1942, and what modern weapon systems accomplish with far greater sophistication today. The human story behind the technological achievement remains compelling. Thousands of scientists, engineers, factory workers, and military personnel contributed to making the impossible real. They solved problems that experts had declared unsolvable. They manufactured devices that combined extreme sophistication with battlefield reliability. They deployed these weapons under conditions of absolute secrecy while facing urgent timelines and enormous pressure. The scientists who redesigned vacuum tubes, developed reserve batteries, and miniaturized radio transmitters accomplished work that would be impressive even today with modern tools and computers. They did it with slide rules, mechanical calculators, and trial and error testing. The factory workers who assembled 130 miniature components into each fuse, working under microscopes while security officers watched, maintained quality standards that modern manufacturing would find challenging. The gun crews who operated 90mm mounts under kamikaze attack demonstrated courage and professionalism that defined the American military at its best. Their collective achievement was to create a weapons system that fundamentally altered the balance of combat power in the Pacific theater during the war's final year. The 90mm gun-firing, proximity-fused ammunition gave American II ships the ability to destroy attacking aircraft at ranges where successful attack was nearly impossible. This capability saved ships, saved lives, and contributed to the successful conclusion of the Okinawa campaign despite unprecedented suicide attacks. The statistical measure of success was clear. Survival rates improved. Ammunition efficiency increased dramatically. Crew confidence rose. Tactical flexibility expanded because commanders could position ships in exposed positions, knowing they had effective defenses. But beyond statistics and technical specifications, the story of the VT Fuze and 90mm gun illustrates a broader truth about how America fought and won World War II. The victory came not from any single superweapon or brilliant strategy, but from the systematic application of industrial power, scientific innovation, and human determination to solving problems that seemed impossible. When British scientists demonstrated that proximity fuzzes were theoretically possible but practically unachievable, American engineers said we will make it work, and backed that commitment with billions of dollars, hundreds of factories, and tens of thousands of workers. When combat experience showed that 5-inch guns could not engage targets at sufficient range to prevent kamikaze attacks, American doctrine adapted, deploying 90mm guns that could engage further and pairing them with fire control systems sophisticated enough to handle the targeting challenge. This pattern repeated throughout the war across every theater and every weapon system. Problems were identified, resources were allocated, solutions were developed, and weapons were deployed, all with speed that adversaries could not match. The proximity fuse took less than 3 years from initial concept to mass production of millions of units. The 90mm gun advanced from developmental weapon to frontline deployment in less than 2 years. This rapid cycle of innovation, production, and deployment reflected organizational culture that valued practical results over theoretical perfection and empowered people at all levels to contribute ideas and solve problems. The sailors who survived kamikaze attacks because 90mm guns destroyed their attackers at 5 miles range owed their lives to scientists who redesigned vacuum tubes, factory workers who assembled electronics under microscopes, logistics personnel who shipped ammunition to forward bases, and gun crews who trained relentlessly to achieve proficiency. Each person in this chain understood their work mattered and contributed to something larger than themselves. This sense of shared purpose and collective effort was perhaps America's greatest advantage in World War II. Not superior individual courage, not better military tradition, not more advanced pre-war technology, but the ability to organize millions of people toward common goals and give them the tools, training, and authority to achieve those goals effectively. The kamikaze threat represented Japan's most innovative tactical adaptation during the war, a desperate attempt to offset overwhelming American material superiority through sacrifice and determination. It was devastatingly effective initially, sinking dozens of ships and killing thousands of American sailors. But America adapted faster than Japan could escalate. The 90mm gun with proximity fuses demonstrated that even against suicide tactics, American technological and industrial capability could generate effective countermeasures. By the war's end, kamikaze attacks remained dangerous but no longer posed existential threat to American operations. Ships survived attacks that would have been fatal months earlier. Crews had confidence in their defensive weapons and training to use them effectively. This adaptive capacity, the ability to recognize threats, develop solutions, and deploy them rapidly enough to affect ongoing operations, defined American military effectiveness throughout the war and beyond. The proximity fuse was not the Manhattan Project. It did not end the war in a single dramatic demonstration. It was something more prosaic and perhaps more important. It was a practical solution to an immediate problem, executed with technical excellence and deployed at industrial scale in time to save lives and win battles. That achievement, repeated across thousands of weapons, technologies, and tactical innovations, was how America won World War II. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.